Hey guys, once again welcome to our channel. In today's video we are going to discuss about the heating curve, and we are also going to cover some new concepts. Let's have a look at them. Yeah, so here you can see clearly here that we are also going to show an understanding of the random motion of particles in a suspension, obviously known as the Brownian motion, as evidence for the kinetic particle model of matter. We are also going to describe and explain diffusion, and we are also going to explain changes of state in terms of the kinetic theory. So without wasting our precious time, let us get started. So let us start with our first new concept, which is about Brownian motion. Now, what is Brownian motion? So let me just tell you a scenario that just happened with me personally. So what happened one day, a scientist was observing a pollen grain suspended in water. Now he realized that the pollen grain was actually constantly moving in random directions. This made the scientist wonder why the pollen grain was moving in this fashion, and he figured it out. Remember the kinetic theory of matter? Particles are always in constant motion. This meant that the water molecules were actually bombarding the pollen grain in random directions to cause the sort of movement observed above. Now, this clearly explains the Brownian motion. Now, Brownian motion is therefore defined as the erratic random movement of microscopic particles in a fluid, example pollen, which I just gave you, as a result of the continuous bombardment from molecule of the fluid, example water molecules. Now, according to this slide, we can see here clearly Brownian motion is defined as the random movement of particles in a liquid or a gas produced by large numbers of collisions with smaller, which are obviously often invisible particles. Now, this observation of Brownian motion proves the correctness of the kinetic particle theory. Let us give you an example how it works. We can see here these large particles are showing jerky and erratic movement, and how they are caused. They're being caused to move. They're being caused to show jerky and erratic movement by these collisions, by the multiple collisions with smaller particles. Moving on to diffusion. Now, diffusion, this is the process by which different gases or different liquids mix, and is due to the random motion of their particles. Now, what happens to diffusing particles? Diffusing particles move from an area of high concentration to an area of low concentration. Eventually, the concentration of particles is even as it spread out to occupy all of the available space. Diffusion happens on its own and no energy input is required, although it occurs faster at higher temperatures. Now, if you look into diffusion in more detail, we call diffusion that movement of particles from a region of their higher concentration to a region of their lower concentration down a concentration gradient. Now, the constant random movement of particles and their kinetic energy allows diffusion to occur. Ultimately, this means particles will spread out from one place to another. There are many things that can affect the rate of diffusion. Molecular mass is one of these things, which we are going to cover in our next video. Now, what happens here? Heavier molecules will travel slower than the lighter molecules. In other words, the higher the molecular mass, the slower the rate of diffusion. We are going to talk about this in more detail in our next video. So let's just move on to let's just continue with our concept. Now, hidden state and kinetic theory. When substances are heated, what happens? The particles will absorb the thermal energy, which is converted into kinetic energy. This is the basis of the kinetic theory of matter, as discussed previously. Heating a solid causes its particles to vibrate more, and as the temperature increases, they vibrate so much that the solid expands until the structure breaks and the solid melts. And obviously, the solid officially becomes a liquid. On further heating, what happens? The liquid substance will expand more, and some particles at the surface gain sufficient energy to overcome the intramolecular forces and evaporate. When the boiling point temperature is reached, all particles will gain enough energy to escape and the liquid boils. These changes in state can be shown on a graph which is called the heating curve. Now, cooling down a gas has the reverse effect, and this would be called a cooling curve. These curves are used to show how changes in temperature affect changes of state. Now, as we discussed in our previous video about in states of matter, what happens if we give a solid energy? Basically, if you are heating it, the particles present in that particular solid, will begin to vibrate more vigorously as they gain more energy. They will absorb thermal energy, and this will be converted into kinetic energy. Now what happens, eventually these particles will begin to separate as they start to overcome the attractive bonds. Eventually these particles will have enough separation to move past one another but still kept relatively close. Why they're still kept relatively close? As attractive forces between these particles will still exist. And what happens? Solid officially becomes a liquid. Now if we come to our third point, on further heating, if we further heat the liquid, these particles will gain even more energy. They will gain even more thermal energy. This means more conversion of thermal energy into kinetic energy, and this will separate the particles even more as they overcome most of the remaining forces of attraction that exists. Now, moving on to our next slide. So before we just discuss this point, I would like to show you some examples of diffusion, of how it works, and I would like to show you a sample heating and cooling curve. So let us just look into it. So now here you can see clearly an example of the diffusion, how it works. So what happens, you can see an example, you can see an experiment we are doing with water molecules and potassium manganate 7. So basically what happens, if firstly we take a beaker, we pour some water, and what happens then, we add potassium manganate 7 crystals. Okay, now if you wait 15 minutes and you will see a change there. What will happen? Potassium manganate molecules will diffuse slowly through the solution from a region of high concentration to a region of low concentration. So now you can see here clearly, at this point you can see there's a high concentration of crystals of potassium manganate 7 solution, and you can see nowhere else there is no concentration of potassium manganate. So we can see clearly diffusion is happening here. So the crystals of potassium manganate 7 are diffusing through this solution of water and crystals of potassium manganate from a region of high concentration to a region of low concentration. You can see here clearly the process is occurring here, and I can also show you a graph here. What happens as the position is increasing, the concentration is also increasing. The concentration is decreasing because it's moving on from A, which is of high concentration, to B, to C, to D, which is of least concentration. Now what will happen if you look back to this beaker, to this solution back after 4 hours? What will happen? The equilibrium will be reached. There will be even particles, even concentration of particles will be now evenly split with their solution. So this proves the diffusion, that diffusion occurs from a region of high concentration to a region of low concentration down a concentration gradient. So now if we move on to our heating curve, you can see here what happens here. Obviously previously we discussed that when solid is into a liquid, when we heat it and the temperature increases, what happens then? This liquid will change into gas as we further increase the temperature. Now what happens if we cool down? If we cool down the gas, the condensation will occur. Gas will change into liquid, the condensation. And if we further cool it further, what will happen? This liquid will change into solid and it will freeze. This is the process of freezing. So you can see here clearly everything is shown here. And also I'd like to tell you that during a state change there is no temperature change. You can see here there is a constant line, there is a straight line here showing that during a state change there is no temperature change. So let us look into more detail. What happens while changing the state? The temperature of the substance remains the same. Why it remains the same? As heat energy is rapidly converted into kinetic energy. This is called latent heat and corresponds to the horizontal sections of a heating or cooling curve. So now we are done with the heating curve. Our next video will be the last part of the particular nature of matter. Stay tuned for that, and don't forget to subscribe, like and share our video, and don't forget to comment down below. Stay tuned for more videos, and I will see you in my next video.